So representing relations, we will learn how to represent relations using matrices that has entries either 0 or 1, or using directed graphs. So there are two ways to represent relations, and actually these two ways will help us in working with relations in general. So as it is written here, so as we see, we will use two methods for representing relations. First method is using 0-1 matrices, and second method is by using directed graphs with arrows with directions. Okay, so we start with the first method, which is using matrices. So how to present a relation from a set A that consists of A1, A2, A3 all the way to AM, to a set B that consists of B1, B2, B3 to Bn. Remember, a relation from a set A to a set B is a subset of A cross B. So it contains, or it consists of ordered pairs. The first element of each ordered pair comes from A, the second element comes from B. So some elements in A are related to some elements in B, and we want to present that some way using matrices. So R can be represented by the matrix, we will call it M sub R, which contains of Mij. Now, what do we mean by this notation? This is the matrix that consists of the following: M11, M12, and we keep going, M13, all the way till M1, sorry, I guess it is M1, and N. What this N is, so I have first row of this matrix to consist of N elements. And what N is, it is the number of elements in the set B. It is here. It is the index in this of the set B. Now, if we continue writing the matrix, the second row, so let me say the first row, pay attention to the first row in here. It is M1, 2, M11, M1, 2, M1, 3, all the way till M1, N. So this I here represent the number of the row. So this is the ith, this is the ith row, this is the ith row. Now, second row is M21, M22, M23, all the way till we reach M2N. So we have N columns, okay? And we keep doing so. If I want to make it clear, let me write more than row. So I have in row 3, first element, M32, second element, M33, third element in the third row, all the way till we reach M3N. So we have N columns. Now, if we keep going till we reach the last row, so how many rows we have? The number of rows here will be the same as the number of elements inside A. I mean, we will continue till M. So the book uses the same notation here, M1. So this is the row number M. M2, M3, and here Mn. And what is this M here? how we decided that the number of the rows is a small m here. It is the number of elements of A here. Okay, and this n, the number of columns, is this element here, which is the number of elements of B. So the number of rows of this matrix is equal to the number of elements inside A. The number of columns of this matrix equals the number of elements inside B. Okay, and now if you go back here, this index J represents the jth column. Represents the jth column. So when we say Mij, we mean the element in the ith row and in the jth column. For example, if we look here, this is the element M23, which means it is the element in the second row and third column. Okay, and here is the element in the third row and second column. Okay, so this is an illustration of what this matrix means. Now when we make this parentheses, square parentheses, then we mean all the rows I and all the columns J, so we get a matrix. Okay, now we go back to represent R with a matrix MR, and what we do, if we find an element AI related to BJ, then we will put in that place in the ith row and jth column, we will put 1. But if they are not related, then we put 0. Now it is better to make this clear, so I will go to the side. Actually, we have an example that helps us to make it clear. Let's go for this example. It is better to do it through an example rather than to do it in general. Okay, now if we have the set A to be 1, 2, 3 and B 1, 2, and now the relation R from A to B contains the ordered pair A, B if A is greater than B. Okay, so A is related to B if A is greater than B. And small a comes from the set, capital A, and small b comes from the set, capital B. So we can actually write the relation in ordered pairs. So the relation R will consist of 2, 1, 3, 1, and 3, 2. Okay, now we will represent the relation this way. We will have A1, let's write it A2, A3. These are the elements of A, and let's write the elements of B, which are B1 and B2. Okay, now, and I mean by A1, A2, A3, this is A1, which is 1, A2, which is 2, A3, which is 3, B1 is 1, and B2 is 2. Now, is A1 related to B1? The answer is no. So we will put 0 in here. Is A1 related to B2? The answer is no. You see, if we go back to the ordered pairs here, this is A2, this is B1, this is A3, and this is B1, this is A3, and this is B2. So that's how they are related. These are the ordered pairs. So, is A2 related to B1? Yes, it is here. So we'll have 1 in here. Is A2 related to B2? No. So we'll have 0. Is A3 related to B1? Yes, we'll have 1. Is A3 related to B2? Yes, we will have 1. So we get this matrix. It is that easy. So we list the elements of A as a column, first column, the element of B, and see whenever an ordered pair is related, then we insert 1. If not, then we insert 0. So this is the easiest way to represent a relation between by a matrix. Now we go the opposite way. In this example, we are giving two sets, okay, and the relation between them is described by a matrix. The question: what is the relation? Can we write the relation as ordered pairs? At the example we have just seen, we have relation given by ordered pairs, and then we produced a matrix representing that relation. Now we go the opposite way. We are giving a matrix that represents some relation, and we are asked to write down the relations in ordered pairs. Now, this is the relation given in here. To make it clear, I copy it here. So the first column to the left, we will list the elements of A. So the relation actually, relation R is from A to B, which means R is a subset of A cross B. So A comes first, so therefore I list it in the column, and then B comes after, so I list it in the row here. So it's B1, B2, B3, B4, and B5. Now we can list what R is. R equals, let's see, where's the one exist? A2 and B1. So A2 and B1 are related. Also, A2 and B1 is this one here. Now this one here is A3 and B1. A3 and B1. Okay. This one here is A1, B2. And for this one here is A2, B2. No, A2, B3. And this one here is A3, B3. And this one here is A2, B4. And finally, this one here is A3, B5. Okay, so this is the relation. Good. Now these two examples are enough to represent what do we mean by representing a relation by a matrix. Okay. So actually, giving a matrix that represents relation, we can find out from the matrix some properties about that relation. I mean, we can decide whether the relation is symmetric, starting from the matrix. We can tell whether the relation is symmetric or reflexive or transitive or none. Okay, we will see. So the matrix on a relation on a set, okay, is reflexive. So now we are saying here we are taking a relation on a set itself, from a set to a set itself. So it is subset of A cross A. So this relation is reflexive if and only if AI is related to itself, to AI. See, it is I in here and I in here, for I equals 1 to n. That means MII is 1. MII means the elements in the diagonal, M1, 1 in the first row, first column, M2, 2, second row, second column, M3, 3, third row, third column. And notice that a matrix for a relation from a set to itself must be square matrix. What do we mean by square matrix? The number of rows is the same as the number of columns. So we have a matrix that has dimension, two equal dimensions. Okay. Now, so it is reflexive if MII equals 1, and which means reflexive if all elements in the main diagonal. So this is a square matrix here, and we have 1 in the main diagonal. Okay, so to have a matrix, a relation being reflexive, we must have 1 at every place in the diagonal. If one place in the diagonal is missed, which means has 0 there, not 1, then that matrix represents a relation which is not reflexive. A relation to be reflexive, then its matrix must contain 1s all the way in the diagonal. And what's about the other places out of the diagonal in the matrix? We can have 1s or 0s in here, no problem, 1s or 0s. We can have anything here. But when we talk about reflexive, we care about what is there in the diagonal. Okay. Now, what's about symmetric? Can we tell from the matrix whether a relation is symmetric or no? Again, we are talking about a relation on a set A from A to A. So we have a square matrix again. Now, the matrix will be reflexive, symmetric, if and only if, this is important, if AI J belongs to R, that means a Ji must also belongs to R. So I need to fix that. This is G. No, the other one is G. This is G in here. This must be G. Okay. So if AJ related to AI, then we must have AI related to AJ. First component related to the second, and then the second must be related to the first in order to say the relation is symmetric. But that means now, to have this belongs to here, that means Mij must be 1 in the jth row I column. And that means Mji must equal 1 in the ith row and jth column. And also it means if we have 0 at one of these, the other will be 0. That means if Aj is related to AI, then AI is related to Aj. That means Mij is 1, then I must get Mji is 1. Okay? But also it means if Aj is not related to AI, then we also must have that AI is not related to Aj in order to have symmetric. But having Aj not related to AI, that means Mji is 0. And then we must have that Mij is 0 also. Okay? Maybe to make it clear for you, too much talking to explain something, maybe a picture worth 1,000 words. What if we have AI at some place here and Aj at some other place? Then we also have AI here and Aj. So we are listing the column, the first column, and the first row from the same set because the relation is from A to A. Now, if Aj is related to AI, that means we have 1 here. So that means I have 1 here. Now, and also if AI is related to Aj, then I must have 1 here. So this is what we are saying now. And notice the diagonal goes from here to here. And what's going on, if we put a mirror in the diagonal, this one will be reflected here, and this one will be reflected here. Good. So Aij and Aj must have the same value. Both are 1 or both are 0. What's about the 0? The 0 means, this 0 means, if they are not related, which means if I have 0 in here, Aj is not related to I, then Ai shall not be related to Aj because we are assuming that we are representing a symmetric matrix. We cannot allow Aj to relate to Ai, but Ai is not related to Aj. We cannot allow this to happen because we are assuming we are having a symmetric relation. So both values mji and mij both must be either 1 or both must be either 0. And actually that means mij must equal mji, and that means the matrix must equal to its transpose. So the matrix R is symmetric, it's symmetric matrix. I'm not sure now if you are familiar with what do we mean by symmetric matrix, or what do we mean by this letter transpose here. So let me go to the side and explain that, what is a matrix and what is its symmetric. It's a transpose. Let A be a matrix. Let's use different letters. Let me use M, because we are using A here for a set. Let M be a matrix. A matrix. The transpose this is S. The transpose of M denoted MT transpose is the matrix which is obtained by interchanging the rows and columns of M. The rows and columns of M. If we take the row, okay, that means if I have this matrix here, which is M. Now, what we do, we take the first row here and put it as first column. So by doing this, we will have that M transpose to be this matrix. Okay. Now we go to the second row and put it as the second column, and so on, till we reach the last row and put it as last column. And actually what we are doing here, starting with the matrix and taking its transposition, actually we were interchanging the places of elements according to their opposite places, according to the mirror. I mean, whenever M is square matrix, I can explain the transpose the following way. When it is square, then there is a diagonal going from the corner to the corner of the matrix. Then taking the transpose means if I have MIJ here, which means MIJ, which means the ith row, jth columns, then this will be moved to its image according to the mirror at the diagonal line. So this will be moved to the place of MJI, IJ to JI. Ith row, jth column will be moved to the jth row, ith column, and the opposite. So these two elements will interchange places, which is the same as saying rows and columns are interchanging. Now, a relation R is symmetric if its matrix is symmetric. I shall write here M, the matrix M is called symmetric matrix, and you shall be familiar with this definition now. If whenever we do the interchanging, which means taking the transpose, then we change nothing. Same matrix still. Same matrix will stay there. What causes this to happen? Because these two elements, every two opposite element, opposite here means according to the mirror and the diagonal, are equal. They are equal. If they are equal, then interchanging places does not change the matrix. In this case, we will see the matrix is symmetric. And this is what's happening for us in here when we represent a symmetric relation using a matrix. When we do so, because every element in Mji and Mij, either path 0 or path 1, so if we change their places, if we interchange their places according to the diagonal, then we change nothing in the matrix, because they are path 1s or path 0s. So a relation is symmetric if and only if its matrix equals its own transpose. So this is T, which means transpose, which means the matrix is symmetric. Okay. Now, the relation is antisymmetric if we have AJI belongs to R. Sorry, if AIJ belongs to R and AJI belongs to R, which means then we must have first coordinate, second coordinate are the same. Which means if first coordinate is related to the second and the second is related to the first, then these two elements must be the same. If they are not the same, then it is not antisymmetric. That means if Mij equals 1, so this goes here, with I does not equal J, okay, then we must have Mji equals 0. We cannot have Mji equals to 1, because that means having these two things equals to 1 means AJI is related, are related, and AJ is related to AI, and AI is related to AJ, so we cannot allow this to happen if we want the matrix to be antisymmetric. So one of them must be 1, and the other must be 0, or path 0. No one is related to the other. Okay? So this is a property of antisymmetric matrix. For example, what's about this matrix here? It represents some relation. So is that relation reflexive, symmetric, or antisymmetric? So what do you think? Is it reflexive? So you notice that there is 1 at every place in the diagonal. So it is reflexive, correct? If one of these ones is not there, which means 0 in its place, then the relation will not be symmetric and reflexive anymore. What's about symmetric? So symmetric, if we take the transpose here and here, then the matrix is not changed. So this matrix is, okay, Sumaya and Kalthum, this is symmetric. It is antisymmetric? No, it is symmetric. The matrix, the relation can be symmetric and antisymmetric. Sorry, it is antisymmetric? No, for sure. And if I write this matrix now, what do you think about this matrix? Okay. This matrix now represent is it a relation which is not reflexive, because we are having 0 here, so there is some element which is not related to itself. Is it symmetric? Not symmetric, Aruba. Not symmetric because this one corresponds to 0 there. It is antisymmetric. No, also Sumaya, not antisymmetric. Why? Because we have I wish I wish I wrote this in different color, not anti-symmetric. Why? Because we have one here and one here, but these two elements are not equal. So again, as another curious question, I want to be in the recorded video. The properties for a relation to be reflexive, symmetric, anti-symmetric, or transitive. These questions, these two properties apply whenever a relation is a relation from a certain set to the same set, from A to A, and then the matrix representing that relation is a square. If a relation is from a set A to a different set B, then we cannot talk about these properties, and we cannot ask about them, okay? Now let's go back to representing relations. So the matrices representing union and intersection of two relations. We want to see how this thing goes. We learned about if we have two relations from a set to another, or from a set to itself, then we can do operation in those relations. We can take the union of these two operations, and we can take the intersections. Remember, relations are subset of A cross B, so they are sets, so we can define union and intersection. Now, suppose we have R1 and R2 relations on a set A, from A to itself. Then and R1 is represented by MR1, R2 is represented by MR2. Now we want to talk about the matrix representing the union. The union, it means it has one position where either MR1 or MR2 has one in that position. So if one exists in the matrix MR1, that means some A is related to some AI is related to AJ. Okay, so when we take that union, then this relation will stay with us. Okay, so wherever we have one in the matrices, the matrix of the union will have one at any of these places. So it is represented here, and this is OR. You remember that 1 or 0. We learned that 1 or 1 will give us 1. 1 or 0 will give us 1. 0 or 1 will give us 1. So wherever there is a 1 at any of these places, we get 1. 0 or 0 give us 1. So we will use that to define the union, the matrix of the union. And the intersection, we will have 1 whenever both matrices have 1 in that place. For the union, either one of them, either this or that. But in the intersection, we will have both. This is the intersection, and we remember what that means. We know that 1 and 1 equals 1, but 1 and 0 equals 0. 0 and 1 equals 0, and 0 and 0 equals 0. So to have 1 in there, we must have 1 at both places. Okay? And thank you for Sumaya for fixing that. This is 0 here. Okay. Yes. Thank you, Sumaya and Modda. Example. Now, these two relations are given with the matrices, so we can compute them for quick. So we will have 1, and for the union here, we'll have 1 everywhere. So the only place which is 0, because we have 0 here, and there is another 0 because we have 0 here and 0 here. And any other place, it has either 1 or 0 in one of the matrices. Now for the intersection, we will have only 1 in this place because we have 1 here and 1 here, and we will have another 1 in this place because we have 1 here and 1 here. And all other places, we will have 0 in these places at one of the matrices. For example, let me use which color now I use? Black. For this 0 here, why we got that 0? Because it is this one and 0 here. So we got that 0. And you can compute that easily. Okay. Good. So we finished representing relations using matrices. Now we will go to represent relations using directed graphs. Okay. So how we do that? A definition. What is a directed graph or a graph? It consists of set of vertices or nodes. So it's vertices together with set E of ordered pairs of elements of V called edges. So for example, we will have A, B, C, D. So these are the vertices. We call them V. The set of vertices in this case is V equals A, B, C, D. Actually, we will learn about graphs in the coming 2 chapters. So this is the vertices. What are the edges? The set E, the edges. They are ordered pairs. So when I say, for example, the edges consist of AB, BD, CD only. If I say those are the edges, let me give them red. That means I will go for AB and connect them. Okay. I will go for B and D, connect them. Then I will go for C and D, connect them. So I got a graph. So it is set of vertices and lines connecting them. Okay. Now the vertex A is called initial, and the vertex B is called initial edge of the the vertex A is called initial vertex of the edge AB, and the vertex B is called terminal. So here I started AB, so that will be an arrow. So we want this graph to be directed graph or digraph, which means we have arrows. So the edges have directions, and directions are important. Now the other one is B from D. So we are going B to D, and then the third one is C going to D this way. So edges, directions, arrows are important. Okay. So the first coordinate is the initial, where the arrows starts, and the second coordinate is the terminal, where the arrow ends. Okay. Now this example make it more clear. Now assume we have the graph that consisted of vertices. So we have V here again to be the set of A, B, C, D, and E consists of these edges. So from A to B, so we will go from A to B. Here we go. This is from A to B. A to D. This is from A to D. Oops. Okay. B to B. Oh, okay. We can connect a vertex to itself, B to B, with an arrow like that. This is a loop. So we'll call it loop. Actually, it is in the definition above. I did not mention it. B to D. Where is B to D? Here we go. B all the way to D. C to A. Where is C to A? Okay, it is from here to here. This is C to A. C to B. Okay, this is C to B. And D to B, going the opposite way. We have B going to D and D going to B. Okay, so these are simply the directed graph, and we can have this as a relation. If we have this as a relation, okay, because your relation is a set of ordered pairs, so we can use them and define a graph for that relation this way. So this, here we go. R is a relation represented by directed graph. The elements of A are the vertices. So actually we could consider this as element of A, and this E as the relation. Okay, good. So let's have more fun by representing this relation as directed graph. Here we go. From 1 to 1, it is a loop here, from 1 to 1. From 1 to 3, we can see it. Where's 1 to 3? 1 to 3, here we go, 1 to 3. From 2 to 1, where's 2 to 1? Here we go. 2 to 3, here we go. 2 to 3 is going this way. 2 to 4, okay, this is 2 to 4. 3 to 1, okay, going the opposite way. So 1 is connected to 3 and 3 is connected to 1. So 1 is related to 3 and 3 is related to 1. 3 to 2, again, 3 and 2. and 4 to 1. Or here we go, 4 to 1. Okay, notice this relation is not symmetric. Why? Because 4 is going to 1, but 1 is not going to 4. So it is not symmetric. It's not reflexive. Why? Because 2 is not going to itself. There is no loop at 2. There is no loop at 3, or no loop at 4. Okay. Now again, another example. What are the order? Okay, we're going the opposite way. In the above example, we have a relation, and then we represent it as a graph. Now we have a graph, and then we want to convert it to a relation. So what is the relation represented by this graph? Let us see. I can see here 1 is going to 4, and 4 is going to 1. I got this. Now to get this, 2 is going to 1, and 2 is going to itself, related to itself. Now to go for that, 2 is related to 3, but 3 is not related to 2. 3 is related to itself because of this loop. Now this going this way and this way, and therefore 1 is related to 3, 3 is related to 1, and 4 is related to 3. Did I miss something? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there are 9 rows in there, including the loops. Okay. Now we will talk about properties of the relation out of their graphs, as we did with the matrices. So giving a graph of the relation. So starting with a graph like the above one. Is this relation symmetric? Is not symmetric. Why? Because 1 does not belong to R. How did I know? Because there is no loop from 1 to 1, so it's not symmetric. Here it says a relation is symmetric if and only if there is a loop. There is a loop at every vertex. I got 2 vertices here that has no loop, so this is not reflexive. As a relation is symmetric if every edge between 2 distinct vertices there is an edge opposite in the direction. So between every 2 vertices there's an edge going from one to the other, and there's another row going to the other to the first. And for example, see here 2 is going to 3, but 3 is not going back to 2, and therefore 2 does not belong to R. I shall here say it does not belong to R, and this causes R to be not reflexive. So R is not symmetric, and this causes R to be not reflexive. What's about antisymmetric and transitive? A relation is antisymmetric if I have 2 vertices with a row going from one to the other and another vertex from going back. So if there are no edges in opposite direction between distinct vertices. Okay. What about transitive? Transitive, if I have an edge going from X to Y, and another arrow going from Y to some other vertex Z, then I must have a vertex going from X to Z. What's about the figure above? Is it transitive? Can we find like 1 going to, here we go, see 2 is going to 1, 2 is going to 1, and 1 is going to 4, 1 is going to 4, but there's no arrow that goes from 2 to 4. So 2 is related to 1, and 1 is related to 4. This belongs to R, but 2 is not related to 4. So it is not transitive. So we can find that from the directed graph. And I believe there's an example below that asks us to decide. So there are 2 examples actually, which brings us to the end of this lecture. Now tell me, is this relation here reflexive? We're talking about this one now. Is it reflexive? Answers. Yes, Muwaddar, it is reflexive. Is it symmetric? Is not symmetric because C is going to A, but we don't have a row going the opposite way, so not symmetric. Is it antisymmetric? Antisymmetric. Is it antisymmetric? Somebody answer. Is it antisymmetric? I'm waiting. Nobody is answering? Muadda, antisymmetric? Notice here, C is going to B, so I have CB in the relation, and B is going back to C, so I have BC in the relation. So I have that, but B is not equal to C. So this causes the relation to be R is not antisymmetric. Correct? B and C, C and B are related to each other, but they are not equal. Okay, what's about reflexive? Is it reflexive? Not reflexive, why? Not reflexive, why? B is related to, maybe B is related to B is related to C, C is related to A, but B is not related to A because there is no arrow going from B and landing to A, so it is R is not transitive. And there's another example, AB, BC, but not AC. AB, no, AB is not there. AB is not there, Muadda. AB does not belong to R because there is no arrow. Be careful. Having a line between two vertices does not mean the two vertices are related. It goes from, sorry, I must say here, this is BA, not AB. BA is not related because there is an arrow going from A to B. That means A is related to B. But there is no arrow going from B to A. So B is not related to A. But A is related to B. Correct? And, okay, yes, B is not related to A. Here we go. Okay, what's about the graph below there? Is it reflexive? Okay. I will repeat that. Mawadda is asking. B is not related to A, right? B is not related to A because there is no, see this arrow I am making in dot, it does not exist. This row exists. It's going A going to B. That means A is related to B. Okay? But going back, there is no arrow that starts with B, initial point, and goes to A. There is no arrow, so B is not related to A. So this is what I'm saying here. B is not related to A. Got it? So I got now here B related to C, because I have a row going from B to C, and C is related to A because I have a row going from A to C. But B is not related to A. Okay. Now what about the... so this is, I got answers, Sumaya and Maria. This not reflexive. Not reflexive because I don't have that. So when I make a row which is dotted, I mean we are missing this. So not reflexive. What about symmetric? Is it symmetric? Yes, Mawadda, it is symmetric. Because every two vertices has edges in both directions. Every two of them. No, sorry. It's not every two vertices has a rows in both direction. No. I'm saying that if there are two, for every two vertices that has an arrow between them, there is another arrow going in the opposite direction. Okay? Notice here, B and D are not related. So this does not go against being symmetric. Okay? So again, I said it is symmetric because every two vertices has rows in both directions. No, this is not true. This was a wrong statement. I should say it is symmetric because for every two vertices that has an arrow, an edge between them, there is another edge, arrow going the opposite way. Okay, so it is symmetric. Is it transitive? Somebody answer me. Is it transitive? Sumaya says no. Is that for my question now? Tell me why it's not transitive. Why it is not transitive? So let's see. A is related to B. A is related to B, right? We can see that. Oh, I want to go B related to A. There might be a different reason for that, but I can see a reason now. But I must write B is related to A, and A is related to C, right? But so B to A to C. What's about B to C? There is no edge connecting B and C, and that gives R is not transitive. What about antisymmetric? Is it antisymmetric? Tell me, somebody answer me. And somebody is saying no for this question also. It is not antisymmetric. Why? Because we can see AB and BA belongs to R, and A is not the same as B. And same AD, same thing, and or AC related to CA, AD related to EDA, and none of them equals the other. Okay, and this brings us to the end. Good, thank you.